Today, we are looking at electromagnetic induction. Electromagnetic induction. From the word induction, induction simply means to make something to happen, or to create something out of another thing. The example of everyday induction or regular induction that comes to my mind now is induced labor. When they say pregnant women go into induced labor, that means that probably it's not yet time for the baby to be delivered, but because of some medical complications, the doctors feel that we have to get this baby out, and then they send the woman into an induced labor. So it was not yet time, but they had to induce the delivery. So induction generally means that something happens that now forces another thing to happen. That's what induction means. Now, when we now talk of electromagnetic induction, it simply means that there is an effect of a field due to the presence of another field. There is an effect of a field due to the presence of another field. So in this case, we have a production of an electric field due to the presence of a magnetic field. So electromagnetic induction, therefore, is the production of EMF, electromotive force, or if you like, induced current. Because when you have an EMF in a complete circuit, currents will flow. So the production of either the induced current or EMF due to the presence of a magnetic field, due to relative motion between the conductor and the magnetic field. I tried to stress this also last week. Now, what this essentially means is that ordinarily, the conductor would not have had currents flowing in it. Ordinarily, the conductor is one. Yeah, Michelle, I'm trying to go over it again. The conductor is one that didn't have current flowing in it. There was no current flowing in the conductor. But you put the conductor in a magnetic field. And because of the presence of that magnetic field, you now have current flowing through that conductor. So it's a production of induced current or EMF, production of induced current or EMF, when a conductor cuts the magnetic field of a magnet. When the conductor cuts through a magnetic field. So that is it. That's what EM induction is like. Now, before now, you will have noticed that we have instances where one field produces another field. We have an instance where an electric field produces a magnetic field. We look at that under right-hand grip rule. Electric field under right-hand grip rule, or under Fleming's right-hand rule also, which is the motor rule. Electric field produces magnetic field. But here now we have a magnetic field now producing an electric field, now producing a flow of charges. So both can happen. Now please take note of this. There is something in physics that we call dynamos. Dynamos. D-Y-N-A-M-O. Dynamo. In physics, a dynamo is simply a device that either converts electrical energy to mechanical energy, or vice versa. A dynamo is a device that converts electrical energy to mechanical energy, or vice versa. So what I'm saying in essence, if you are following me, I want to believe that one of you, at least some of you will now have been able to pick that both generators and motors are therefore essentially dynamos. So both your generator and your motor are both referred to as dynamos. Because any device that converts electrical energy to mechanical energy or vice versa is a dynamo. Now, when the energy conversion is from electrical to mechanical, we call that an electric motor. When it's from electrical to mechanical, that's electric motor. But when it is from mechanical to electrical, that is a generator. Either way, both of them are called dynamos. So I think that we have to get that, understand that concept clearly. Understand it clearly. Now, you're going to have instances, maybe in IGCSE, where the question will ask you what the function of maybe some parts of your electric motor is. You are going to have that. Now, let's look here. Let's look at this diagram of the electric motor. You have carbon brushes. You can see the carbon brushes here. You have carbon brushes. These rings that have positive sign here, negative sign here, are carbon brushes. And then these copper rings, these golden yellow rings, there are two of them. Even though the two of them are essentially half of one. So all the copper rings there are essentially just one ring, but we have split that one ring into two. So both of them are called split ring commutators. So we have therefore a carbon brush and a split ring commutator. Now please take note of this. What is the function of your split ring commutator and your carbon brush? Can anyone tell me that function? Anyone else raise up your hands to tell me the function of the split ring commutator and the carbon brush in the electric motor? Anyone? Okay, Unuma. I've seen Unuma's hand. Let's look for Unuma. Okay, all right. Unuma, yes, talk to me.
Okay, so from the video, it said that the carbon brushes and the commutator that have the split structure will help the thing to flip because when it reaches this part, it has to turn over again, and the wires will be like tangled if it doesn't flip it back. Yes.
Okay, thank you, thank you. Let me also hear from one other person. I've seen Fisoye's hand. Fisoye. Yeah.
Okay.
Let me hear you.
Like Onuma said, they help to flip the current that is flowing through them.
Good. They help to flip the current. So what we are essentially saying for everyone who needs to have a better understanding of this, what we are saying is that, okay, Anissa, I like your response. I've seen your response here too. That's good. Now, what we are saying is that if you look at this, you have your current flowing in the direction of these arrows. That's like the anti-clockwise direction now. It's flowing to the positive terminal. When it flows in like that, it flows in into the armature. This blue part of the diagram is what is called the armature. It's actually a conductor. So it flows in, you can see the blue arrow showing how it's going. It's flowing in like that, and then comes out this way. Now, when it flows in, because of Fleming's left-hand rule, because of the direction of the force. We have our north to south in this direction. We have our north to south of the arrow, that's the field. We have the current flowing up. Current is flowing up. And then we have the force acting down. Now, what happens is that when the commutator now, when the force acts on the armature, and the armature now goes down, this side, the right-hand side goes down, the right-hand side, left-hand side goes up. It will get to a horizontal position. I mean, it's a vertical position. It was at a horizontal position before. It will now get to a vertical position. Upon getting to a vertical position, something has to happen so that that motion can be continuous. So what happens is that there must be a change in direction of current. There must be a change. Something must create a reversal of the direction of current so that the force that was acting downwards before will now act upwards. And the one acting upwards will now act downwards. So what the carbon brushes do is that they are the ones that create that change in direction. If you look at this now, the commutators, envisage these two copper rings. These copper rings, as the armature turns, they too will turn. So it will get to a point that the armature that was here, that my arrow is pointing on, and this armature will make contact with the left side commutator, while the one that was on the left side before will come and make contact with the right side. So when that flip of contact takes place, the current direction reverses. That reversal of current direction is now what creates the direction of the force that also reverses. And that thing happens very fast. That is why your motor is able to continue turning. Otherwise, if there was no commutator, the motor would just have turned, reached a vertical position and not be able to turn any further. So that's essentially the function of the split ring commutator. Now, the function, again, Femi, the function of the split ring commutator is, okay, though I should not worry, but you've gotten it, but I'll just say it again. Function of the split ring commutator is that in addition to the carbon brushes, the split ring commutator reverses the direction of current so that the direction of the force can be reversed and the motor can continue to spin. The motor can continue to turn. Both of them work together. The commutator and the carbon brush work together. So let's take note of that. So we have thought about dynamos. We've said that both the generator and the motor are dynamos. Both of them are dynamos. And now we have looked at the motor. Now, let's go further. We have already explained what electromagnetic induction is, but I want to stress something here. Even though we know that one field, whether magnetic or electric, can produce the other field, one field can produce the other one, we define electromagnetic induction in terms of a magnetic field producing an electric current. So the convention, so to speak, is that even though an electric field could as well have produced a magnetic field, and a magnetic field could also produce an electric field, when we are defining electromagnetic induction, we define it in terms of a magnetic field producing an electric field due to relative motion between conductor and magnetic field. So when you are defining EM induction, don't define it in terms of electric field producing magnetic field, but in terms of magnetic field producing electric field. I hope that is clear. I hope you are all clear so we don't make that mistake. Oh, okay, somebody is still asking me about the commutator, about the carbon brush. Okay, I should say it again. Okay, I will say it again. The commutator, the split ring commutator, in addition to the carbon brushes, the split ring commutator, in addition to the carbon brushes, reverse the direction of current. Reverse the direction of current flowing through the armature reverse the direction of current flowing through the armature so as to reverse the direction of the force on the armature. So as to reverse the direction of the force on the armature and create continuous motion of the motor. And create continuous motion of the motor. Let me go further to say that this is done by the split ring commutators switching the carbon brushes they make contact with every half turn. This is done by the slip ring commutator switching the carbon brushes they make contact with every half turn. I want to go back to that diagram. There is a diagram. So the commutators, they switch the carbon brush they make contact with. This is the carbon brush. So the commutator that was making contact with the carbon brush on the left will now make contact with the carbon brush on the right. While the one on the right will not make contact with the one on the left. Every half turn that happens, and then the revolution continues. That's how that is done. Anissa Akorede Sedo, I need to know if you are now clear. Asma, are you now clear? Anissa, redefine. You said redefine. Okay. Maybe I should just explain it and allow you to write it down in your own words. Thank you, Korede. Anissa and others again. Oh, okay, Asma, I'll come back there. Now, okay, Anissa is now okay. Okay, thank you, Anissa. Now, for the EM induction thing, what I'm saying is that anytime you are defining electromagnetic induction, you always define it as magnetic field producing electric field. Don't define it as electric field producing magnetic field. That's what I'm saying, Asma. Define your EM induction as magnetic field producing electric field due to relative motion between the conductor and the magnetic field. Asma, that answers your question. Even though, if you look at it, you will say that both of them are EM induction. You could say that because if a magnetic field, if current flows, it generates magnetic field. That's some form of induction taking place. But when we are defining EM induction, we define it in terms of magnetic field producing electric field. Now, let me explain that further by going to this diagram we have here. This is a conductor. This is a generator principle. This is a conductor. This conductor doesn't have a battery. If you look at it very well, this conductor doesn't have a battery in it, meaning that there's nothing that is supplying current here. But the conductor is cutting through the magnetic field. So it is the magnetic field that now produces the current flow, that induces current. That is how we define EM induction. Asma, please confirm to me that that is clear. Sedo, electromagnetism is just defining interaction of both the electric field and the magnetic field. That's just it. When you say electromagnetism, it's just the interaction of the electric field and the magnetic field. A joint interaction of both fields. That's it. Anissa, due to the relative motion between the magnetic field and the conductor, due to relative motion between the magnetic field and the conductor. I'm answering questions as they are dropping in the chat box, so others too can drop their questions there. I take the questions as I go on. All the questions I've been answering are as they are dropped in the chat box. So please make use of that opportunity as well. Now, quickly now talking about generators. In our homework, we already looked at how to increase the size of induced voltage. I will not go back to that. But what I want to say essentially is that while the motor, okay, somebody asked me a question about to define electromagnetism. That's what I defined, Joel. Somebody said I should define electromagnetism, and I've defined it as just the joint interaction between electric and magnetic fields. Yeah, Unuma, and I said we will get back there. Now, for the generator, while the motor uses the principle of the left-hand rule, the generator uses the principle of the right-hand rule. I mean, both are Fleming's rule. Motor is the Fleming's left-hand rule. Generator is the Fleming's right-hand rule. But it's the same principle, actually, the same thing, the same process. Just that in this case, it is based on your right hand. So, the Fleming's right-hand rule helps us to know that the induced current, what will happen? In what direction will it be? Now, when you induce the voltage, you have, when you increase voltage, induced voltage, you are essentially increasing the induced EMF. EMF and voltage are essentially the same thing. They only have marginal differences in terms of where you are measuring from. Unuma, that answers your question. EMF and voltage mean the same thing. So when you think of EMF, think of voltage. And when you know that voltage is something that usually supplies power for the circuit, supplies current. So charges move. Voltage, the battery is what will push charges through. So currents flow as a result of the presence of a voltage, of an EMF. So when you have a higher voltage, then you have a higher current, a higher induced current. So when you increase induced voltage, you increase the size of the current too that flows. Now, to get higher value of voltage or current as it were, the principles to use are what we already have and which many of us already know. So Fleming's right-hand rule uses the principle of generators. Let us take note of that. Use the principle of generators. While the left-hand rule is for motors, right-hand rule is for generators. Take note of that. Now, having said that, you have what the right-hand rule states. You have it here, right there on your screen. I hope you all can still see it. You have Fleming's right-hand rule right there on your screen. For the right-hand rule, the only thing that actually changes is that we now have an induced current as against the current that was originally flowing for the left-hand rule. In the right-hand rule, the current is now induced, but they still mean the same thing. All the fingers still mean the same thing. The thumb is still for motion, the forefinger is still for the magnetic field, the second finger is still for current. Just as in this case, it is now the induced current. It is the induced current. So, that is good now. This is the Fleming's right-hand already stated. It's already stated for you. I will implore you all to go and study it once again. Now, both rules, explaining both rules are usually part. Thank you, Anissa. Explaining both rules are usually part of what IGCSE asks you for, particularly the part of the carbon brush, split ring commutator, and then they will ask you which one is the motor rule. The motor rule is the Fleming's left-hand rule. The generator rule is the Fleming's right-hand rule. I expect that someone will be taking that one so that you note it down. Motor rule, that's for Fleming's left hand. Generator rule, that's for Fleming's right hand. Now, Fleming's right-hand rule is not the same thing as the right-hand grip rule. Please, because you hear right hand, don't think I'm still referring to right-hand grip rule. Right-hand grip rule is different. Fleming's left-hand rule, that was the one for, that's the motor rule. That's the one that electric motors work with. Fleming's right-hand rule is the one that generators work with. Michelle, I'm answering your question now. Fleming's left-hand rule is the motor rule, is the one that electric motors work with. But Fleming's right-hand rule is the generator rule, is the one that generators work with. Now, before I round off, I want to also tell us that there are two types of generators that we can also have. Even though my time is running out, let's see if you can quickly do this. For generators, we can have AC generators and DC generators. For generators, we can have AC generators and DC generators. Take note of that. AC generators and DC generators. When you get to year 12, you are going to do a topic called simple AC circuits. But to just give you a paraphrase, AC just means alternating current, alternating. So the generators that we all use in our houses, when our distribution companies take light, those ones are AC generators. The ones we use in our homes, they are all AC generators. They are the ones that produce alternating current. But there's also another type called the DC generator. Now, basically, in the diagram for generators and motors, what is the difference that is there? The difference that is there is very simple. Just one very simple difference. Let's go back to that diagram for motor. Now, this is the diagram for the electric motor. This is one for electric motor. Now, this same diagram is also what the AC generator uses. I mean, the DC generator also uses diagram. But for the AC generator, rather than having a split string commutator that is broken into halves like this, it has two full slip rings. That's for the, what I'm saying now is for the AC generator. The AC generator, rather than having two halves of commutators, it has two full slip rings. Slip rings. A full ring like this carbon ring here. If it was not broken into two, if it was complete, it would be a slip ring. It would be called a slip ring. Commutator comes from the word that we are trying to swap them to commutate. But if it was not like that, it would be a slip ring. Now, an AC generator has two full slip rings like that. Two of them. That's what an AC generator has. So that one will produce current in one direction, while the other will produce current in the reverse direction. That's just the difference between the both of them. And good for you, questions don't really bother much about that. Now, so I think that we can safely now wrap it up and say that we have essentially have a better or more grounded knowledge of this. But I should say something in your homework. A number of us still didn't convert our centimeters to meters. For that number 4, centimeters to meters, you need to convert. That's not right, we don't convert. And then I asked some people to mention 3 ways of increasing the induced EMF in a straight conductor. In a straight conductor, in a conductor, increase the induced EMF in a conductor. Good. So I saw some people telling me that I should increase the number of turns. And then the issue I have with that was that, is it not a coil that you can increase the number of turns? If a conductor is just a straight conductor, you cannot increase the number of turns for that yet. So to increase the number of turns on anything, you must first turn that thing into a coil. You must first turn that into a coil. So I'm going to stop sharing here. Hoping that I will have just a few minutes to just take maybe just 1 or 2 questions, and then we'll call it a wrap. I have seen a number of chats. Yeah, Laura, I saw your message from you, but Laura, what can we do? Laura, drop your email address so that I can send the video of this class to you. I cannot upload it on our platform because it's going to take so much space. It will be heavy. But if you send your mail, I may send it to you. I could send it to you so that you can catch up. Yeah. Okay. Okay, Tare, you too. All right, no problem. Send the mail. Send the mail. Don't send it here. I cannot see you. Send it to me via the online portal. Don't send the email here. Email here. Send it via the online portal, and I'll send the videos to you. Yeah, that's good. I hope any question. Asma, yeah, you to send your mail. Any other question? Okay. I'm sure you all are waiting for my merit points question today. So my merit point question for today, for all of you, about the 3 ways assignment. I don't understand. Unuma, we'll get to that later. Now, take down this question. This is for everyone. I want you all I'm putting it down in your chat box, so it will come up for you, to come up for all of you. Yeah. Mention 2 types of transformers and what they are used for. Yes, I'm expecting responses as we wrap up the class. Okay, I have from Unuma. What are they used for? Only Unuma. Okay, I have Ayomikun, I have Fisoye, I have Korede, Ayomikun, Fisoye, Korede. Okay, I will pardon some of you. Temitope, what do you mean by core type? All transformers have a core. All of them have a core. The size may be different, but they all have a core. Michelle, polyphase. Polyphase. No. Polyphase transformers. You are giving me types in terms of the phases of transformers. No. Michelle, think again. Okay, I've seen Ayomikun zone, I've seen Unuma zone. Okay, are they doing okay? Are they doing? Sedo, look at your chat box. The question is there. Daniel, no. No, what you have given me, Daniel, is both of them are on each type of transformer. So I want the 2 types of transformers. Nwachuku, okay. Nwachuku is okay. Ifeoluwa, electric power transformers. All transformers are electric power transformers. Bemisayo, yeah, yes, Bemisayo, Nwachuku. I see some people going online. Some people are going online to give me answers, and what I'm looking for is not what you are telling me. Anissa, I disagree. Okay, Tokpe. Michelle, yeah. Michelle, you got it in. Ifeoluwa, you got it in. Good.